All right, on my watch, it's 2 minutes past 10, so I'd suggest for everyone who is on time that we begin with this presentation. Anyone else can just follow up. Anyway, I would like to bid you all a very warm welcome to today's webinar. My name is Alina Dübeler from the company Enginesoft, and I will be your host for today. Before we begin with the actual presentation, I would like to say a few short words about organizational details up front. In order to guarantee a presentation without any interruptions, we are going to turn your microphones on mute. I'm just going to go ahead and do that real quickly. I kindly ask you to keep this setting for the course of the webinar, as interruptions are going to eventually make it hard to keep track of the contents we are going to present. If you have any questions coming up, please feel free to use the chat to communicate us your questions in writing. At the end of the webinar, we will make time for a Q&A session where we will answer as many questions as possible. What I also recommend to you for optimal audio quality is the use of a headset. Our experience has also shown us that a poor internet connection will have a negative effect on the audio quality, so we recommend you to make sure your internet connection is reliable. Last but not least, it is usually the case that the overall audio quality is a lot more reliable when you join the meeting via web instead of dialing in via phone. This being said, let us have a look at the agenda for today's webinar. Today we have 4 short presentations planned for you by 2 different speakers, whom I will introduce to you in a second. This session should take roughly about 45 minutes, depending on how much time we will spend on the Q&A session in the end. I will just give you a quick moment to read through the agenda before moving on to the introduction of the speakers. All right, I think this should do. Right, so first I would like to introduce you to Mr. Martin Hallmann, from whom you can expect 2 presentations today. Mr. Hallmann currently works as a research associate at the Institute of Engineering Design of the Friedrich-Alexander University, Erlangen-Nürnberg, and we are very grateful that he has agreed to share his expertise with us and all of you in this webinar. Welcome, Mr. Hallmann. Perhaps you'd like to give a small wave so everyone can see you with your camera turned on. There we go. Moving on to the other speaker of today's webinar, whom is Mr. Florian Weidenhiller from TTC³ GmbH, which is a sister company from Enginesoft. He is currently employed as a technical director and is an expert in terms of tolerance analysis. Hi, Florian. We are glad to have you. I don't know if you want to give a small wave too, so everyone can see you. There we go. This being said, I would now like to pass the moderation rights on to Mr. Hallmann so the actual presentation can begin. There we go. You should have the rights now.
Yeah, just a short minute. So I think that everything works fine so far. Thank you, Mrs. Dübeler, for the kind introduction. So as it was said before, my name is Martin Hallmann. I'm a research assistant at the Institute of Engineering Design at the Friedrich-Alexander University in Erlangen in Germany. And my research work mainly focuses on the combination of tolerance simulation and optimization. And to lose not too much time here, we will directly start with a brief introduction on the fundamentals of optimization and its application in product development, and especially in tolerance design. So in general, when we are designing a product, we have to consider a number of different aspects and interests at the same time. So there's a multitude of different design aspects, such as manufacturing, product quality, costs, or sustainability, just to mention a few here, and they are all summarized under the term Design 2 or Design 4X. And in this context, we have to keep in mind that when we design a product for a specific goal, such as for quality, we also directly or indirectly influence other aspects, such as the manufacturing costs. So consequently, a design for a specific goal always implies the design to meet specific requirements and constraints. So the development of a good product requires to solve the conflict between various objectives, but also constraints. And in the last years, the pressure in terms of quality and cost was severely increased. Companies have to assert themselves on international markets, and these markets are dominated by short times to market cycles. So a good is not really good enough in modern times, and only best optimal solutions can help us there in order to survive in today's fierce competition. And to find these best solutions, we can use mathematical-based, optimization-based design methods in order to get the best out of our design. So by definition, optimization can be understood as the act to obtain the best results for a specific problem under given circumstances. And in order to find this best design and the best values for our design variables by optimization, we have firstly to formulate our problem correctly, and secondly, solve this problem with the aid of a powerful optimization algorithm. And in general, an optimization problem can be structured into three main elements. The first one is the so-called objective. It is the goal of the optimization, the global aim, and it has to be described by a mathematical function, the so-called objective function, and this objective function is minimized within the optimization workflow. So in case of a car brake system, for example, it can be the braking time to stop the car we want to minimize. At second, we have to define a set of constraints. The constraints are a set of equality and inequality constraints that are further conditions which have to be fulfilled within the optimization. So otherwise, the solution would not be valid. It would not be feasible. So if we exceed, for example, a maximum disk temperature or a contact pressure, we could not assure that our product will function. And last but not least, there are the design variables, which are our control factors, for which we want to find the optimal combination of values within given lower and upper boundaries. So the designer wants to find the best values for geometrical, but also non-geometrical parameters. And for this case, for example, the disk diameter or the coefficient of friction. So keeping this basic idea of optimization and this basic formulation of an optimization problem in our mind, we can go a step further and transfer this idea on tolerancing. And in doing so, optimization can help us to find the best tolerance values for our tolerance design. And this is also called optimization-based tolerance allocation in theory. And in doing so, we can basically differ between two different interpretations of tolerance cost optimization. If the focus is more on a least cost tolerance design, it's a cost-driven design, then the global aim is to find a suitable combination of tolerance values that can minimize the resulting manufacturing costs. So the objective corresponds to the manufacturing costs. But we also want to ensure that a predefined quality limit is not undercut, so we are defining the constraints, the quality as our constraints. So this corresponds to a design for cost and a design to quality approach if we keep in mind the definition from the first slides of my presentation. And in contrast, in quality-driven tolerance cost optimization, objective and constraints are flipped. So we try to get the best quality for a predefined limit of costs. However, regardless of the type of optimization, statistical tolerance simulation plays always a key role in the optimization, either in the constraints or in the objective, in order to assure that the total product quality under variation can be assured. And at this point, I will give the word to Mr. Weidenhiller, who will present the fundamentals on statistical tolerance simulation in the following minutes.
Yes, thank you, Mr. Hallmann. I'm gonna go ahead and pass those moderation rights on to Mr. Weidenhiller.
Yes. All right, thank you very much. So let's talk some minutes about statistical 3D tolerance simulation, especially in my case in CETOL software. So in order to run a statistical 3D tolerance simulation, the first step is to get the right input information for the tolerance simulation. In order to get the right input, we use dimension management and methodology to extract all the necessary information from product development to include in our tolerance simulation. What are these input factors? First of all, it's the quality. It's one of the most important things we're looking at. And we can differentiate between a so-called functional quality and a perceived quality. Functional quality is the internal quality. Are all the parts, do all the parts fit together? Do we have any rework or scrap, and can we avoid unnecessary tight tolerances and so forth? Now, the perceived quality is something the end customer sees. It's functional quality, but it's visual quality as well. For example, the gap and flush situation between headlamp and hood in automotive industry. So that's one input we have to include in the tolerance simulation. The other input is the variation. Now, talking about variation, we differentiate between so-called manufacturing variation and assembly process variation. Manufacturing information itself is deviation due to production of a single part, and this deviation occurs because of manufacturing processes like tuning, milling, deep drawing, and so forth. That example, you can see we have a profile tolerance of 2.6 with respect to a certain datum reference frame. In the other case, we have a profile tolerance of 1.8 with respect to a datum reference frame of ABC. Now, this manufacturing variation already has an impact on the final position of a part. As you can see here, the diameter has an impact on the position of the pin, as well as the height or the width of this slot, or the angle of the slot here. All these tolerances, and in combination as well, they influence the final position. They have an impact on the final position of the pin in that case. Now, the assembly variation is a variation which comes out of the assembly process. Assembly variation occurs through part orientation. As you can see here, this was a primary vertical part orientation, and the same part here is in a primary horizontal orientation. Another impact is the assembly sequence, which means the way parts are coming together in assembly. The way fixtures are influencing the part orientation and the assembly sequence, and the float at the end of the day. Float is something very interesting because it can happen in different ways. As you can see, it can happen due to gravity, external forces. It can induce a rotation of the pin in the hole. So these are all the variation inputs for the statistical simulation. And here, once again, the dimensional product requirements, manufacturing requirements, and perceived quality. Now, if you are coming to the Six Sigma solution approach for tolerance simulation, all these informations that you've seen, just quality, part orientation, assembly sequence, tolerances, and assembly float, they are applied in the simulation model. What happens in the simulation itself is that one tolerance out of all the tolerances is chosen, and this tolerance varies its position. Now, out of this variation of one tolerance, while all the other tolerances are freezed, leads to a certain impact of this tolerance on my measurements. And out of the impact of the measurements, a so-called sensitivity of the tolerance on the measurement can be calculated. Now, this is repeated for all tolerances, and the result of this approach is that we receive a so-called sensitivity matrix. The sensitivity matrix for each measurement shows the calculated sensitivity of each tolerance in the measurement. Out of this sensitivity matrix, the statistical parameters are calculated. Statistical parameters like standard deviation, mean shift, skewness, and kurtosis. The distribution curve is fitted in order to meet these statistical parameters, and the so-called quality metrics are calculated. Quality metrics are CP and CPK value, process capability. The typical results of a statistical 3D tolerance simulation look like this. One result is the range in the measurement, and the range in combination with the design limits that you can see here deliver a certain out of spec. And this out of spec is a very important value in order to deduce the CP and CPK values, the process capability values. The next result of the statistical 3D tolerance simulation is the contributor. So as you've seen in the result before, we have a certain percentage out of spec here. And the engineers, they want to know, why does that happen? What is responsible? Which tolerance, which assembly sequence, which assembly float is responsible for this percentage out of spec? And this impact is shown in the contributor report, where you can see each tolerance with its specific percentage value, it impacts on the tolerance simulation. In this example, the first contributor has an impact of 45.54% of the results. The second biggest contributor is 19%, and the third is 15%. Now in the simulation results, we not only see the contribution itself, but the sensitivity. The sensitivity is the direction of the tolerance. For example, if the tolerance varies in one direction, if the impact is positive, the measurement varies in positive direction as well. For a negative sensitivity, as we can see here, if we have a positive tolerance variation, we can see a negative impact on the measurement. So that's about it in a nutshell about a statistical 3D tolerance simulation. And I transfer the presentation rights back to Alina.
Yes, thank you very much. I'm going to go ahead and transfer them back to Mr. Hallmann so the next part of the presentation can continue. There you go.
Yeah, perfect. So far we've heard the basics on optimization-based tolerance design and on tolerance simulation. And in this part of the webinar, I will show you how tolerance simulation can be embedded in the optimization workflow. And besides theory, I will also illustrate this application by coupling Teamcenter with VSA and MATLAB. So tolerance design corresponds basically to the last step of the product development process. So after defining the concept of a product and defining the nominal values for our design parameters, we have to do the tolerance specification, as we've learned in the previous presentation of Mr. Weidenhiller. And we also have to define the values for the tolerances in order to limit the single geometrical part variations. However, this task is dominated by the already discussed conflict between cost and quality. So if tolerances are chosen too tight, the total product quality is overfilled, but at cost of the manufacturing costs. And yeah, in contrast to loose tolerances will decrease the total manufacturing costs, but the number of non-conform assemblies will increase and quality criteria cannot be met. So it is the critical point to find the optimum. And yeah, the optimum is where tolerances can meet the functional requirements and also minimize the resulting manufacturing costs at the same time. And in doing so, optimization can help us to accelerate and optimize the search for our least cost tolerances. So having a look on the basic workflow on this slide here, we can see that the start is usually a tolerance design with too tight tolerances, mostly because of fear. So yeah, these tolerances can easily fulfill the quality criteria, but they lead to high manufacturing costs. And this initial tolerance design serves as a basis for the optimization-based tolerance allocation approach now. So yeah, firstly, we are generating, or the optimizer generates a new set of tolerance values based on an initial guess or on previous optimization runs. And yeah, for these currently chosen tolerances, cost analysis is performed in order to help us to predict the resulting manufacturing costs, while the tolerance analysis element here helps us to evaluate the fulfillment of the quality criteria. So we are getting both information on cost and quality at the same time, and both serves as the basis in order to evaluate our current solution. So firstly, it is checked if the predefined quality criteria are met, and secondly, at which cost. And this loop is repeated until we meet a termination criterion, such as the total number of iterations, for example. And yeah, then we finally will get a tolerance design that leads to least cost, but also can fulfill the functional requirements. So if we have a closer look on this tolerance analysis module here, and we are using sampling techniques, we can see that there are some sub-steps here in our workflow. So in the first steps, we have to virtually generate the part variations with respect to the currently allocated tolerances. And these virtually parts are then randomly assembled. And afterwards, we have to analyze the assembly response for each of this combination of our samples. So we have to evaluate it by a suitable function. It is called the assembly response function, and as a result, we will then get a probability distribution, as we've heard before, and this serves as the basis in order to decide if we can fulfill the functional requirements or not. And therefore, we're using a quality metric such as a process capability, but we can also use a non-conformance rate or a scrap rate, which corresponds to the percentage of non-conform assemblies. So in tolerance cost optimization, and especially in sampling-based tolerance cost optimization, it is quite common to stick on the non-conformance rate in small parts per million in order to be in accordance to the Six Sigma philosophy for industry. So far, this presented approach works perfectly if we can explicitly describe the assembly response by a mathematical function. So if we have a look on this driving pulley here, for example, and we want to analyze the influence of the size tolerances on the gap between the pulley and the fork here, we can easily describe the interrelations by a linear vectorial function here. So it's not that big deal. It is quite easy for this case. However, the definition of this function can become very difficult, or in my opinion, even impossible if the problem gets more and more complex. So in most practical problems, we have to take geometrical tolerances into account. We have to deal with nonlinear effects. So world is not only one-dimensional, and we have to consider these nonlinear effects in tolerance simulation. And part compliance can also be can be important if it has a significant influence on the on our system behavior. So just to mention a few aspects here, depending on the type and complexity of our problem, it is necessary to predict our system behavior numerically by simulation. And in doing so, the assembly response is then indirectly defined by simulation. So getting back to our approach, and if we want to embed this or apply this implicit formulation of the assembly response function, we have firstly to differ between two implicit black box model approaches. So the first idea is that we replace the assembly response function with a black box and use the help of a numerical solver, a finite element model, or a CAD model, or anything else in order to analyze the system behavior under variation. However, we can also draw the black box around the total tolerance analysis approach and element and directly replace the tolerance analysis by any existing tolerance simulation software, such as 3DCS, RDNT, or CETOL 6 Sigma, which will be in focus in the next presentation. And yeah, so it is possible to easily embed tolerance simulation in our workflow here. And in the remaining minutes, I will exemplarily show you how we can integrate Teamcenter with VSA in our optimization workflow. So just one back. So if we want to embed VSA in the optimization framework, we have to ensure that our optimizer is able to adapt the tolerance analysis model to the currently chosen tolerances. So for all of you who are familiar with VSA, it is also possible to export our model in an ASCII-based text file. So it contains all information on the tolerance simulation and information on our assembly conditions, on virtual measurements, and of course also the tolerance specification, including all specified tolerance values. So the optimizer has to identify the relevant sections in our text file and must be able to replace the initial tolerance values by the newly allocated tolerance values in each optimization step. Afterwards, it is allowed to call VSA by command within the updated input file. So tolerance simulation runs in the background and an export file is generated which contains all single measurement values for the relevant measures. And this export file is then re-imported in the optimization, and product functionality can be evaluated by a chosen quality metric, such as the already discussed non-conformance rate or process capability. So VSA is called externally in each optimization step as a black box model in order to analyze our probabilistic assembly response for this current solution. So far for the theory, to show its practical application, we come just back to our driving pulley example here. And yeah, if we are using VSA, we have to define so-called virtual measurements in order to analyze or to assure total product quality. And for this case, I've chosen to have a look on the tilting of the pulley as a critical measure within the given range of 1 degree here. And I've also put another measure here to assure that there's no clamping between the pulley and the fork with an lower specification limit here. So in the next step, we have to define or do the tolerance specification. And yeah, I've exemplarily chosen some flatness tolerances and parallelism tolerances here. We also have a perpendicular tolerances just to show its functionality here and yeah, to show its applicability of the approach. And I've also applied some size tolerances, but they are set as fixed. So it is also possible to define or to tell the optimizer that he's not allowed to modify every tolerance which is specified. Moreover, we have the opportunity to define so-called setup reductions. So we can also tell the optimizer that he should set some tolerances equal. So yeah, this is a good idea in order to reduce manufacturing setup costs. So after defining the tolerance analysis model, it has to be exported as our text file, which is then used as an input for the optimization. And this optimization is done in MATLAB using a genetic algorithm here. And it's a good idea to use this optimization algorithm since it's a meteoristic optimization algorithm and it can handle these black box models very well. Yeah, in addition, we need a cost model, and this cost model is needed in order to map the tolerances and the resulting manufacturing costs as a function. And yeah, this functions as our objective function in the optimization. And the total manufacturing costs are the sum of all individual manufacturing costs as a function of the individual tolerance values. So for this example, I've just chosen the cost functions fictitiously, but if you want to apply this approach in industry and in practical use, you have to gather the manufacturing data and set up the cost model based on real manufacturing data. For a simulation, I've chosen the Monte Carlo simulation in VSA and 10,000 samples here, and we want to assure that a quality requirement of 2,700 ppm is not exceeded. So this corresponds to a ±3 sigma range here. So if you're having a look on our optimization results, we can see that the optimizer was able to iteratively minimize the resulting manufacturing costs. So we took about 130 iterations here, and we can see that this approach corresponds to a design for cost approach, as we've learned in my first presentation, and that the total non-conformance rate was pushed to its maximum limit of 2,700 ppm, but the constraints are not violated. So our solutions are feasible here, and we can see that this is the design to quality element in our approach. So the total number of VSA cores was approximately 6,500 here, and we had a lot of virtual measurements in the background, and it took approximately 6.5 hours for the total combination of simulation and optimization. So to sum it up, the benefits of our total approach is that it's application independent. So we have the free choice of tolerance simulation tools, and the approach is easily adaptable to the user's needs. So it is fully automizable to a level that no programming skills are needed. And in summary, this leads to a very powerful tool, which makes it usable for design engineers and not only tolerance experts with in-depth knowledge in optimization, statistics, and programming. So yeah, in this webinar, I've only showed a small part of my ongoing research works. So if you are further interested in the theory of tolerance cost optimization, please feel free to have a look on my open access publications. And all of you who are more interested in its practical application or want just to get more details personally, feel free to contact me after the webinar via email. And last but not least, I'd like to thank you all for your attention, showing interest in the research, and I'm really looking forward to your questions, thoughts, and also helpful advices, I hope, in the upcoming Q&A session at the end of this webinar. Thank you a lot.
Yes, thank you very much, Mr. Hallmann. That was a great presentation. And lucky for you, we already do have a few questions that came in, so you can look forward to that in the Q&A session. But before we get to that, let me just pass the moderation rights back to Mr. Weidenhiller for the last presentation of this session. There we go.
Okay, can you hear me? I guess you can. My microphone is switched on. Yes, thank you, Mr. Hallmann. Very interesting approach that you presented us with VSA software. I'm going to show you an example now of the combination of CETOL software in combination with the optimizer modeFRONTIER. So in my example, I'm going to show you if it works or not. Here we go. I'm going to give you a brief introduction about the tolerance analysis that we performed on this switch lock assembly. And in the next step, I'm going to give you a quick overview of how the optimization was done in modeFRONTIER. And I'm going to finish with an overview of the results where I can see how the tolerancing looked before the optimization and how the tolerancing looked after the optimization, and how we can reduce the cost of a total assembly. Now, let's have a look at the assembly that we're looking at the switch lock. This is an assembly of altogether 10 parts. You can see we have a back plate where a switch is assembled to via a pin, We have another latch rider here, which is assembled with a pin here as well. And we have the switch lever on the very bottom, which is assembled to the backplate via another pin. Now, as you can see here, the kinematic is quite complex because the latch is guided by the back plate and is guided by the big switch and the switch lever as well, because this latch here is connected via these two clamps, clamp 1 and clamp 2, to the other parts. So altogether, as I said, we're looking at 10 parts here, and talking about tolerances. So for each part, you have approximately 5 tolerances in this assembly. So we are talking about an overall of 50 tolerances approximately here. Now, what we are looking at is 2 design positions or 2 kinematic positions. We have the on design and we have the off design. The difference is in the different kinematic setup. You can see here in the on design, the switch is rotated to the left and the switch lever and the other parts are pushed into their respective positions. In the off design, the switch lever is turned to the right and all the parts are pulled in their respective positions. Now, what is the quality we want to look at? Quality is always the first step for tolerance simulation. So in on design, we want to look at the gap between these 2 parts here, at the minimum gap here between the switch and the lever. And we want to look at the distance here from the back plate to this lever here, distance A. In off design, we want to look at the contact here between these 2 switches, and we want to have a look at the distance here, distance A, the same distance, the same measurement we looked at in on design. So overall, we have 4 measurements we're looking at, and that's where we run the statistical simulation. And the results of the statistical simulations look like that. You know what happens in statistical tolerance simulation? I told you that before. The tolerance vary during assembly, and the impact on the measurements is calculated. What we can see here is out of our 4 measurements for on design and off design, we have 2 measurements that you can see here, the gap and the contact, which have CPK values which are lower than 1.33. Our design intent was to make a simulation model where all the CPK values are 1.33 or bigger. As you can see here, we have a CPK of 1.7 and 2.1. These 2 CPK values are okay, but these 2 need to be optimized, as you can see here below in the overview as well. Now, looking in the next step at the contributors of these 4 measurements, there's one thing which is very interesting to see, and this is typical for tolerance simulation. Very often, contributors not only occur in one measurement, but they're also participating in other measurements as well. As you can see here, for example, the blue measurement or the blue tolerance is the main contributor of 3 measurements, and measurement number 6 for the first one. The green contributor is participating in all measurements as well as the yellow one. So for our approach here, we said that we are going to look at all the tolerances of our contributors which are higher than 4%. In that case, it means out of our basically 50 tolerances, we are looking at a total of 17 contributors in that case. Now, next step is the optimization. And in the optimization, we're going, first of all, have a look at the targets we're looking at. As mentioned before, the primary target of our simulation is to ensure that all CPK values are bigger than 1.33. That means in our case, we have to tighten tolerances, we have to tighten the highest contributors in order to reach the CPK value of 1.33. The next target is we not only want to reach the goal of CPK value 1.33, on the other hand, we want to reduce the production costs by increasing small tolerance values. So on one side, we want to decrease tolerances in order to meet the CPK value. On the other side, from bottom up, we want to increase tolerance values in order to reduce the production costs. So let's have a look at the workflow within modeFRONTIER. This is a very simple setup. So in modeFRONTIER, we usually have a logical workflow where the simulation software is coupled to the optimizer, and we have the data workflow of all our input data. The input data we're looking at in our case is the tolerances that we specified out of our contributor reports. If you remember, we have 17 tolerances that we want to look at, and these 17 tolerances are listed here, and they are the primary input. Another data input is the output, the measurements itself. We're looking at 4 measurements here, and we have the total cost of our total assembly. We have an objective. Our primary objective is to minimize costs, and we want to minimize the costs against our constraints, and the constraints are the CPK values, which means no CPK value smaller than 1.33 is allowed in our case. Now, before we run the simulation, we have a look at the cost function as well. In our case here, we used a simplified cost function. The cost function here shows the value of the tolerance with respect to the cost of the tolerance, which means a high tolerance, for example, a tolerance value of 0.4, as you can see here, has a cost factor of 4, whereas a tolerance of 0.1, you can see has a cost factor of 10. And now the total production cost of one assembly or of one design alternative is the sum of all the single costs of each tolerance. Now, running the optimizer, we receive different optimization results. The first result we see is the so-called history chart. In the history chart, we see our different designs with respect to our absolute values. And the values of each design, they converge against the CPK value of 1.33. For example, if you look at the light blue measurement, the CPK value of the light blue measurement here starts with a very low CPK value. But during the different design changes that the optimizer is looking at, the CPK value gradually converges against the desired CPK value of 1.33. The next result is the so-called parallel coordinates chart. In this parallel coordinate chart, each design that we're looking at is a single line. And the horizontal lines you can see here are the different constraints we're looking at, the CPK values of the 4 different measurements, and the cost, the total cost. Now the parallel coordinates chart only looks, as you can see, at the optimized tolerance designs. So we're not looking at CPK values which are lower than 1.33. We're only looking at CPK values here in that chart which are greater than 1.33. Well, for example, if you look at the design, the Brown design, we have CPK values 2.4, 2.3, 1.4, 1.4. So the CPK values are okay, but for the Brown design, we have a very high cost range of 172. Now this looks a little bit confusing. What we can do is here, we can take the slider of the cost here and just look at the small cost zone between 120 and 127. Now all design alternatives which are not within this cost range, they are great, and we only see 2 designs which are left, which fit the minimum cost function here. And the one design with the least cost is design 708. So altogether we had approximately 750 designs that we are looking at, and design number 708 was the most cost-efficient design. Looking at the specific results, on the top you can see our original GD&T layout of 2 parts here, the backplate and the switch. And in the lower section you can see the optimized design, the optimized tolerance design. So we have some examples where the tolerances needed to be decreased. We had to tighten the tolerance value from 0.4 to 0.25. Here in the profile tolerance, we had to decrease the tolerance of the position from 0.4 to 0.15. The other position from 0.3 to 0.2. But on the other hand, we were able to enlarge the tolerance here, the profile tolerance, from 0.2 to 0.45, and the other position tolerance here from 0.2 to 0.45. Now, doing this via hand in a tolerance simulation could take quite a lot of time, and it's a pretty tedious work. And with the optimization, we can do that all in one. So we started with the original failing CPK values of 0.26 and 0.99 and a cost factor of 135. And our optimized design, all our CPK values were reached, the targets were reached, and the overall cost of the whole design was reduced from factor 135 to 123, which means a reduction cost of 9%. So that's all from my side. Thank you very much for your attention, and I will forward the presentation rights back to Alina.
Yes, thank you. Thank you, Florian, for this presentation, and thank you everyone for paying attention up to this point, even though we ran over just a little bit, considering we scheduled this webinar for 45 minutes. However, we would still like to make time for the Q&A session that we promised, since you did send us some questions through the chat. So I'm just going to have a quick look at it. I hope you can all see my screen at this point. All right. Mr. Hallmann, we have one question for you here. It says, the optimization time for the given example of the pulley driving assembly was mentioned to be about approximately 6.5 hours. What are the main contributors to the total optimization time, and is it possible to reduce the total runtime?
Okay, yeah, this is a very good question. So for this special case of the integration of external torrent simulation software, it is, or it mainly depends on the implementation and the time it takes to call the external software in the background in combination with the in and export of the information. But in general, there are three main contributors, I would say, which makes an effect on the total optimization time. So first of all, we should try to cut the total number of function evaluations and set them as low as possible. So the choice of the sample size has got a great effect on the results. And therefore we can use enhanced sampling techniques such as latent hypercube sampling or importance samplings, for example, in order to decrease the total simulation time. Secondly, we have to try to reduce the time to evaluate a single sample response function by a thoughtful selection of the degree or the detailed degree of our tolerance analysis model. And at third, we should try to scale the total number of optimization iterations down by a proper selection of the optimization settings, as well as the termination criteria. So when we finally combine and harmonize these single countermeasures, it can really help us to reduce the time for optimization, I would say, to a tolerable size here. Yeah.
All right, perfect. Thank you. That was very, very thorough and detailed. So I think that question should be answered all right. Let me just
hopefully, yeah.
Yeah. There's still some more. Let me pass one question on to Florian real quick. It says, in the switch log example, 17 tolerances out of approximately 50 were simulated. What are the differences regarding modeling and simulation time if all 50 tolerances are used?
Thank you for the question. It's halfway answered by Martin Hallmann, what he said before. I mean, the simulation time of modeFRONTIER just depends on the number of parameters that we include. So you have to find a certain border of parameters that you use for your optimization. We could certainly use 50 parameters as well, but that's not, the simulation time is not a linear scaling, because if we have more parameters, we have more design possibilities, and the simulation time of the optimization depends on the simulation time of the simulation, the 3D simulation at the end of the day. So to answer the question, with this run we're looking at with 17 tolerances, we are looking at a simulation time of approximately 5 hours, what we had. And if we're increasing that to 50, it would be probably a lot more. So it is possible. It's no problem from optimization side. The only question is it necessary? And that's why you always, before you start the optimization run, you always have gotta have a very close look at the parameters that you're looking at, and you have to decide intelligently which parameters you're using.
Thank you. Thank you very much. That seems clear. Let's try to do one more questions each for you guys. We still have a few left in the chat, so maybe we can wrap it up around 11. Let me see. Mr. Hallmann, there's one more question for you. In your given example, the tolerance cost functions are chosen fictitiously. Where and how do you get the cost curves for industrial applications, and have you already made experience with real manufacturing data?
Since the cost functions correspond in sum to the objective function, it is very decisive that they fit to the given problem. So you do always have to gather the information with respect to the given use case and the given manufacturing conditions by experiments. So we did some studies in the past with a supplier in the automotive industry, and we've developed some methods in order to efficiently gather the necessary empirical data. And we also gave some advices to provide them by mathematical functions. And in addition, we are currently working on approaches to efficiently set up these cost models for additive manufacturing, so for new manufacturing techniques. However, yeah, it would go, I think, beyond the scope here to go too much into the detailed workflows in this Q&A session. Yeah, but if anyone is more interested in this other big jigsaw piece, I would say, of tolerance cost optimization, yeah, just feel free to come back to me so we can discuss these aspects in detail. I would really appreciate this. Yeah.
Yes, thank you very much. Also, your contact information were on the presentation earlier, and if anybody still has questions left and did not note them down, you can just contact me. I think you have my email address via the emails you have received so far, and I'll be happy to provide you with the contact details of Mr. Hallmann if need be. All right, thank you. Let's look at one last question for Florian. There's actually a few more questions left. Unfortunately, since we are running over already, we're not going to be able to answer all of them today, but we will get back to you personally in the next few days to answer whatever questions we do not answer right now. Florian, I've got one for you. Is the assembly float included in the tolerance simulation as well? And can the float be optimized as well?
Yes, of course, the float is included. It just didn't show up significantly because we have very tight float situations here in that log switch, but it certainly shows up. And if it shows up bigger in the contributor reports, we can certainly optimize the float as well in two ways. We can either modify the nominal diameter of pin and hole, or we can modify the diameter tolerance of pin and hole. So the float can be included, and it can be included in different ways into the optimization.
All right, I see. Thank you very much. All right, well, I think this sums it up for today. Thank you very much, everyone, for your participation and for your attention. Thank you, Florian. Thank you, Mr. Hallmann, for your presentations. This webinar has been recorded, and we will make this recording available to everyone by tomorrow morning. If you would like any further information or maybe receive the actual presentations, feel free to get in touch, and we will be happy to forward the material to you. This being said, thank you very much, and have a great day, everyone. Goodbye.
Thank you. Bye-bye.
Thanks for having me. Bye.
Thank you.